This video is going to cover empirical and molecular formulas, and the goals for this video are to understand the difference between an empirical and molecular formula and to learn how to figure out empirical and molecular formulas from experimental data. So first, let's go over some definitions for empirical and molecular formulas. So the definition of an empirical formula is the formula of a compound expressed as the smallest possible whole number ratio of subscripts of the elements in the formula. And the definition of a molecular formula is the formula of a compound in which the subscripts give the actual number of each element in the formula. Now those are kind of your formal textbook definitions, so let's take a look at what these definitions are really talking about. First, let's take a look at molecular formula. The key thing to focus on in the definition here of a molecular formula is actual number of each element. So a molecular formula is telling us the actual number of each element in the compound. So if we look right here, I have a picture of a compound that includes the elements carbon, hydrogen, and oxygen. Now, if we count how many of each element is in this compound, that will be our molecular formula. So let's do that. Let's take a look at carbon atoms first and count them. So there are 1, 2, 3, 4, 5, 6. 6 atoms of carbon. So that 6 becomes our subscript right here by carbon. Now let's count hydrogen. There are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 atoms of hydrogen. So I'll put a 12 down here. And finally, let's count oxygen. There are 1, 2, 3, 4, 5, 6. 6 atoms of oxygen. So this right here is our molecular formula because the subscripts 6, 12, and 6 are telling us the actual number of each element that are found in this compound right here. So from this molecular formula, how do we figure out the empirical formula? Now, the key word in the definition of empirical formula is ratio. So empirical formulas are expressing ratios. So to figure out what the empirical formula of this molecular formula is, we have to take a look at the subscripts down here. Specifically, we have to ask ourselves, are these numbers reduced? Or is there a greatest common factor between them that we can use to reduce them? So if we look at the numbers 6, 12, and 6, we need to ask ourselves, what is the biggest number, or is there a biggest number that goes into both 6 and 12? And in this case, there is. There's the number 6. The number 6 is the largest number that divides into 6 and 12. If there wasn't a greatest common factor, then this molecular formula would also be the empirical formula. But since there is a greatest common factor, there's going to be a different empirical formula. So we decided that the greatest common factor is 6. So what we do is we divide each of these subscripts by that greatest common factor of 6. And once we divide, that is going to be the empirical formula. So if we look at carbon, 6 goes into 6 once. Now we don't write a 1 here because the C by itself is just an understood 1. If we look at hydrogen, 6 goes into 12 twice. So 2 becomes our new subscript for the empirical formula. And finally, if we look at oxygen, 6 goes into 6 once. So again, we just write O. This right here is our empirical formula because it's telling us there's a 1 to 2 to 1 ratio. So if I give you a list of formulas here, for example, C2H4, CH2, C4H8, and C6H12. Okay, and if I ask you which one of these four is an empirical formula and which are molecular formulas, the question you need to ask yourself is, are any of the subscripts fully reduced? And if they are, that is your empirical formula. The ones that are not reduced would be molecular formulas. So if we take a look at the subscripts in all of these formulas, we see that this one right here is in reduced terms because there's no number that goes into both. Remember, there's an understood 1 here, 1 and 2. We can't reduce it any further. So this right here is an empirical formula. The rest of these, if you look at this first one, C2H4, there's a greatest common factor of 2. So this would be a molecular formula. Down here, 4 and 8, there's a greatest common factor of 4. And then finally, 6 and 12, there's a greatest common factor of 6. So all these are molecular formulas, but once you reduce them, you end up with this empirical formula. So of these 4 formulas, this one right here in the box is an empirical formula, and the other 3 are molecular formulas because they are all following this 1-to-2 ratio. Now let's take a look at types of questions that you will be asked about empirical and molecular formula. The first type of question we're going to look at is finding a molecular formula when you're given an empirical formula and a molecular weight, because that's probably the easiest question you'll be asked. So the molecular formula of a compound can be determined from the empirical formula if the molecular weight is given. So you can figure out a molecular formula, but you need to be given 2 pieces of information. You need to have the empirical formula and you need to have the molecular weight. If you don't have both of these pieces of information, then you cannot figure out the molecular formula. So let's take a look at this first question. The empirical formula of hexane is C3H7. Its molecular weight is 86.2 AMU. What is the molecular formula of hexane? So we can answer this question because we're given those 2 pieces of information. We're given an empirical formula of C3H7 and we're given a molecular weight of 86.2. So we're looking for a molecular formula. So we're looking for a formula that is going to tell us the exact amount of each type of element in the compound. This empirical formula, C3H7, is telling us a ratio. So how do we figure out the molecular formula? We figure out the molecular formula by using this formula. We do the molecular weight divided by the weight of the empirical formula. So I'm just going to abbreviate here. So empirical formula weight. Now, if we look in the question, we see we're given a molecular weight. It tells us right here the molecular weight is 86.2 AMU. So that's the number that goes in our numerator. But now we're missing an empirical formula weight. So what we need to do is we need to find the atomic mass, the weight of our empirical formula, which is C3H7. And we do that by the same skill we learned earlier on in the chapter. What we do is we look at carbon and we see how many carbon atoms we have. So we have 3 carbon atoms. And we times that by the atomic mass of carbon, which is 12.01. And then we add that to how many hydrogen atoms do we have? We have 7 hydrogen atoms. And we times that by the atomic mass of hydrogen, which is 1.01. Now remember, we get these 2 numbers from the periodic table. So when you put that into your calculators, you should get 43.1. So that is the weight of our empirical formula. So this number here goes into our denominator. So now when you divide 86.2 by 43.1, the answer is 2. So this number 2 right here is telling us that we need to multiply the subscripts in the empirical formula by 2, and that's going to give us the molecular formula. So our empirical formula is C3H7, but I need to multiply both of these numbers, these subscripts, by 2. So that means we have C6H14. And this right here is our molecular formula. So that is how you figure out a molecular formula when you're given an empirical formula and a molecular weight. Now the next type of question we're going to look at is how to find an empirical formula when we're given percent masses. Now this is by far the most popular type of empirical formula question. And to figure it out, there are 4 steps that we need to follow. And I highlighted the 4 steps in different colors because I'm going to highlight the work in that corresponding color so you could follow along a little bit easier. So the first step is to change the percentages to masses in grams. The second step is to take those masses and convert them to moles. So to do this, you need to be comfortable converting masses to moles. The third step is to divide by the smallest number of moles. And the fourth step is to multiply those numbers until you get whole numbers. Now the fourth step you might not have to do in every problem. It just depends how the numbers to step 3 work out. So you might have to do step 4 and you might not. Now the steps, how I wrote them, kind of have a nice little ring to it, so it might help you remember them. So percent to mass, mass to mole, divide by smallest, multiply until whole. Super corny, I know, but it might help some of you. Okay, so let's take a look at how to solve a problem like this. So the two elements that are mentioned in the problem are magnesium and nitrogen. So we know that the formula we're going to have at the end is going to be Mg with some subscript and N with some subscript. And what we're looking for are what those subscripts are going to be. So step 1, change the percentages to masses. And this is most definitely the easiest step. So what we do is we take the percentages that were given in the question, which are here 72.2% and 27.8%, and we just rewrite them as masses in grams. So for magnesium, I'm just going to write 72.2 grams, and for nitrogen, I'm going to write 27.8 grams. So that is step 1. Now, step 2 says to convert these masses to moles. So we convert masses, specifically grams, to moles by using the molar mass of those elements found on the periodic table. So for magnesium, in 1 mole, there are 24.03 grams. Now remember, I'm getting this 24.03 from the periodic table. I find magnesium on the periodic table, I look at the number that's written under it, and that's the number that I'm using here. Same thing for nitrogen. In 1 mole of nitrogen, there are 14.01 grams. Okay, when I put this to the calculator for magnesium, I get 2.97 moles. And for nitrogen, I get 1.98 moles. Okay, so that is step 2. That is converting the masses to moles. Now, we need to take a look at these two numbers of moles, and we need to see which one's smaller. So 1.98 is smaller than 2.97. So I'm going to divide both of these numbers by 1.98. So divide by 1.98, divide by 1.98. And for nitrogen, when I divide 1.98 by 1.98, I get 1. And when I divide 2.97 by 1.98, I get 1.5. So this is step 3. Dividing by the smallest number of moles. Now, step 4, multiply until whole. In this example, I need to do that because I have a 1.5 right here, which is not a whole number. Now, if we had did this calculation and it was 1.9, I can round that to 2. Or if it was like 1.1, we can round that down to 1. But because it's like right in the middle, it's 0.5, we cannot round it. And also, when we write our empirical formula, I can't have 1.5 magnesium to 1 nitrogen. We can't have partial numbers. We need whole numbers. So what we have to do is we have to think about what can we multiply 1.5 by to give us a whole number. Now, a lot of times, this is just trial and error. So you can just start with the number 2 and work your way up, and eventually you'll get a whole number. So if we do 1.5 times 2, that gives us 3, which is a whole number. So that's it, we're good. But because we multiplied this top one by 2, we also need to multiply the bottom one by 2. So whatever you do to one, it's like algebra. Whatever you do to one side of the equation, you have to do to the other. It's the same thing here. If you multiply one of the elements by a number, you have to multiply all of the elements by a number. So in that case, we get 2. So this is step 4. Multiply until whole. So now these numbers right here, these numbers are going to be the subscripts in our empirical formula. So our empirical formula is Mg3 and 2. And that is the answer. Let's try another problem. So this problem says a compound consists of 40.92% carbon, 4.58% hydrogen, and the rest oxygen. What is the empirical formula? So let's take a look at the elements we have here. We have carbon, we have hydrogen, and we have oxygen. So step 1, let's change our percentages to masses. So carbon, we have 40.92 grams. Hydrogen, we have 4.58 grams. And oxygen, well, we're not given a percentage for oxygen, so we have to figure it out. So these 3 elements together need to equal 100%. And we're given 2 percentages, so from those 2, we can subtract them from 100 and get the percent of oxygen. So if we take 100 and we minus 40.92 and then minus 4.58, we get 54.5. And so that is the mass of oxygen in this compound. So you might be asked a question like that, where you're given the masses of everything but one, and you have to figure that last one out. So just know that the compound as a whole needs to equal 100%, and to find that missing element, you just subtract whatever you're given from 100. Okay, so this is step 1, changing our percentages to masses. Now, step 2, we need to convert these masses to moles. So, in 1 mole of carbon, there are 12.01 grams. In 1 mole of hydrogen, there are 1.01 grams. And in 1 mole of oxygen, there are 16.00 grams. Okay, now when I put these into the calculator, for carbon, I get 3.407 moles. Now when you do these numbers, try to give yourself at least 4 significant figures, because sometimes the number of moles will be really, really similar, and it might only differ by like 1 number way back here. So if I only give myself 2 or 3 significant figures, it would appear as if 2 of the moles were actually the same number when they're really not. If you have more significant figures, you'll see those differences easier. I found that I've always been safe with 4, so 4 is probably your best bet. So if we look at hydrogen, that will give us 4.534 moles, and oxygen 3.406 moles. Okay, so now we have converted our masses to moles, and that is step 2. Now, step 3 is to divide all of the numbers by the smallest number of moles. Now, if you see here, it's a good thing we gave ourselves 4 significant figures, because 3.407 and 3.406 are really close, but 3.406 is smaller. So we're going to divide all 3 of these numbers by 3.406. Okay, let's see what we get. Now, of course, this one, oxygen is going to be 1. When we divide this, we also get 1. And when we divide hydrogen, we get 1.3. Okay, so this was step 3. Divide by smallest amount of moles. Now, since again we don't have 3 whole numbers, we need to figure out what number can we multiply 1.3 by to get a whole number. Let's just start with 2. If I do 1.3 times 2, what does that get me? 2.6, and that is not a whole number. So let's try 3. 1.3 times 3 is 3.9, and we can round 3.9 to 4 because it's a 0.9. So I'm going to multiply this by 3, which gives me 3.9, which we can round to 4. But because I multiplied 1 by 3, I have to multiply everything by 3. Okay, and this is step 4. Multiply until whole. Okay, and so these numbers right here, 3, 4, and 3, become my subscripts in my empirical formula. So the empirical formula from the percent masses that we were given is C3H4O3. And that is our answer. Let's take a look at one last problem, which is probably a step up in difficulty from the previous two. So this problem says, caffeine has the following percent composition: carbon 49.48%, hydrogen 5.19%, nitrogen 28.85%, and oxygen 16.48%. Its molecular weight is 194.19. What is the molecular formula? Okay, so now if you remember from the first question that we did, I said that in order to find out the molecular formula, you have to be given 2 pieces of information. And those 2 pieces of information are the empirical formula and the molecular weight. So we can take a look here, and in the problem we're given a molecular weight, but what we're not given is an empirical formula. So before we can find the molecular formula, we have to find the empirical formula from the percent composition that we're given in the problem. So what elements do we have here? We have carbon, we have hydrogen, we have nitrogen, and we have oxygen. So step 1, change all of the percentages to masses. So 49.48 grams, 5.19 grams, 28.85 grams, and 16.48 grams. So this is step 1. Now step 2 says that we have to convert all of these grams, these masses, to moles. So in 1 mole of carbon, there are 12.01 grams. In 1 mole of hydrogen, there are 1.01 grams. In 1 mole of nitrogen, there are 14.01 grams. And in 1 mole of oxygen, there are 16.00 grams. Okay, now let's punch these numbers into the calculator. So for carbon, I get, with 4 significant figures, 4.119 moles. For hydrogen, I get 4.98 moles. No, I'm sorry. I get 5.138 moles. For nitrogen, I get 2.059 moles. And for oxygen, I get 1.03 exactly moles. Okay, so this is step 2, converting the masses to moles. Now, step 3, dividing by the smallest number. So of these 4, 1.03 is the smallest number. So I'm going to divide all of these by 1.03. And when I do that, for carbon, it comes out to 3.99, which we can round to 4. hydrogen comes out to 4.98, which we can round to 5. Nitrogen comes out to 1.99, which we can round to 2. And then oxygen, of course, is going to be 1. So this is step 3. Dividing by the smallest number of moles. Now step 4, multiply into a whole. Well, we already have whole numbers, so in this case we don't have to do step 4. So these numbers right here become the subscripts in the empirical formula. So the empirical formula is C4H5 N2 and O. Okay, so now we have that missing piece of information that we needed to figure out the molecular formula. We have the molecular weight from the problem here, and now we have the empirical formula. So if you remember, to figure out the molecular formula of something, we divide the molecular weight by the empirical formula weight. So we have the molecular weight, which was given in the problem, and that's 194.19. And we need to divide that by the weight of our empirical formula right here. And so to figure that out, you would just do 4 times the atomic mass of carbon, 5 times the atomic mass of hydrogen, so on and so forth. So if you figure that out, it comes out to 97.11. And when we do that, when you divide these two numbers, you come out to 1.99, which can be rounded to 2. Now, what we do with this number 2 here is that we multiply each of the subscripts in our empirical formula by 2, and that will give us our molecular formula. So for carbon, 4 times 2 is 8. For hydrogen, 5 times 2 is 10. For nitrogen, 2 times 2 is 4. And for oxygen, 2 times 1 is 2. So this right here is the answer to the question. This is the molecular formula. Now that's probably as difficult as the questions will get. So if you can handle that, then you should be good to go. So this video covered empirical and molecular formulas.